the tool itself does not generate or rarely generates false positives. On the other hand, an anomaly detector, by its nature, generates false positives. It's impossible to do anomaly detection without false positives. What you can do is to try to keep the false positives low and the detection rate high, but you cannot do no false positives. Which means that, combined with the fact that when you see a snort rule firing, you know that that specific attack has been performed. When you see an anomaly detector fire, you just know that something is wrong. But what is wrong is your guess. So basically, you cannot use anomaly detectors, really, for automated reaction, while you can use misuse detectors for automatic reaction, if you are so inclined. That's what's been marketed as intrusion prevention systems. So, in the universities, we work a lot on anomaly detection, basically because misuse detection is simple. It's difficult to engineer it and to create a product. It's not like ISS or Real Secure. It's not like ISS builds Real Secure and that's easy. It's a difficult product to build. But scientifically, it's not challenging to create rules and to create products that apply rules. Scientifically, it's challenging to create systems that do not need rules. And in particular, my research has been in the area of unsupervised learning. What is a learning algorithm? It's nothing fancy. It's nothing like Star Trek. A learning algorithm is an algorithm which gets better over time at doing whatever it's supposed to be doing. Because it learns, it stores information extracted from the data. In some cases, what you're using are supervised training algorithms. How many of you do use a spam filter? Any type of spam filters? I don't believe it. Raise your hand. Who uses a spam filter? So the other people do not use email, right? Your favorite client-based spam filter, by Easy and Spam Filter, whatever, usually has a button with which you flag spams that it did not catch, and with which you flag things that it incorrectly classified as spam. That's called a supervised learning algorithm. You give an example to it, and it learns from the example. You pre-classify things for it. You correct it over time. That's a supervised learning thing. Unsupervised learning is even more mysterious. It means that the algorithm sorts out things by itself. You don't give it examples. You just obtain results. It's not magic, it's mathematics, actually. There are two particular classes of unsupervised learning algorithms that I'm sure you will be as interested as me, no, probably not, in knowing. Outlier detectors and clustering algorithms. Let's see them briefly. Clustering algorithms are algorithms that can put together things that are similar and separate things that are not similar according to a set of features. This is a very, very nice definition, but it has two weak points. First weak point is, what do you mean by similar? Which implies defining a distance. And the second weak point is, according to a set of features, a set of observations. So what are the sets of features? Because, for instance, if I observe the current climate in Milan and the current climate in Kuala Lumpur, in Milan, there may be 35 degrees, as there are in Kuala Lumpur currently. It's not like that, actually. It's much colder in Milan. But the two climates are not defined by this single variable. So if I look just at the temperature and I said, okay, I will dress in Kuala Lumpur exactly like I would dress in Milan, I will be making a very, very horrible mistake. First of all, because in Milan, during the night, temperature changes. In Kuala Lumpur, during the night, it's almost as warm as during the day. Because it's different climate, because you have to take into account different variables, different features. If you're trying to cluster objects, to cluster things, and you take into account the wrong features, you will end up with a wrong clustering. First thing. Second thing, even when you have features, in particular, if the features are not described by numbers, calculators badly suck at dealing with features. So if you have something which is green, and something which is blue, and something which is red, what is more similar between these three objects? As a human, you will probably say, well, it's three different colors, right? A computer cannot tell it that way. Or, for instance, if you have different colors and you want to group them by shades of color, you have to find a way, which can be your regular RGB way of describing colors, in order to let the computer calculate the difference between colors, which is something that we humans give for granted, exactly as we humans take for granted that I can see this thing over there, which is slightly obliquous, the other which is not obliquous, and call them, those are two chairs. And if I see outside a totally different one, I will say that's still a chair, because it has some common features with the other chairs of the world. It's very natural for me as a human to think like that. But to teach a computer how to call a chair is not easy. It's a whole field of research in the field of artificial intelligence. Yeah, I don't have the time to go through all the details. But the problem, basically summarizing it, is there is a number of algorithms that are useful to make a computer distinguish among things. And if you look at the literature on intrusion detection, all those algorithms, sooner or later, have been applied to intrusion detection with varying results. What we did was actually take someone, who was me, with some knowledge about how computer security in the field works, and taking some other person, which is still me, who actually studied how the mathematics behind these algorithms work, and put those two things together. And the outcome was quite satisfying, or at least it was worth a PhD degree, if that's any measure for you. I'll get to the actual algorithms and to the method in a moment. I just wanted to introduce the second big part of the things that we use, which is outlier detection. What does outlier detection mean? What's an outlier? An outlier is something which is so different from the other things that you observed that you think that either it's an error or it's been generated by something totally different. Basically, the idea comes from industrial sensors. If you have a sensor which is measuring the temperature at some point in an industrial plant, and it says 100, 100, 100, 1,500, 100, 100, that 1,500 probably is a glitch. It's an outlier. It's something that you either want to explain in some context or you want to discard because it's evidently wrong. So, what's an outlier, for instance, in network traffic? The whole point of my work was trying to understand if this hypothesis holds. If we look at packets, at network packets, as observations, are attacks outliers? Because if they are outliers, I can detect them in some ways. If they are not outliers, if they statistically blend in with the rest of the traffic, then all the literature on intrusion detection done by using network traffic in an anomaly detection sense is rubbish. Well, turns out that it's not rubbish, luckily for me. What turns out is that if you look at the packets as what is called a multivariate time series, so a multivariate time series is a series of values, of sets of values that you measure. A time series is, I measure temperature here in Kuala Lumpur over a day, once every 10 minutes. I have a time series of temperatures. A multivariate time series is, I measure temperature and humidity here in Kuala Lumpur once every 10 minutes. It's a bivariate time series. Detecting outliers on univariate time series is simpler, of course, than detecting them over multivariate time series. The problem is that we have excellent algorithms for detecting outliers on multivariate time series that are made of real numbers, where real is used in the mathematics sense. But if our values are made up of those non-numbers that I was talking about earlier, yellow, green, red, or if you prefer, TCP versus IP versus ICMP, or if you prefer, TCP packet bound to port 80, 81, 8080, these are not real numbers. They are not even integer numbers. They are numbers that qualify a port. Okay? So it's not true that port 20 and 21 are closer than port 21 and 22. Not necessarily. So the whole idea is to find an outlier detection algorithm that works also on categorical data. And the impressive thing is that after extensive research on literature, I found out that basically there was no algorithm that could fulfill my expectations, but one which was almost what I needed. It's called Smart Sifter. It's been developed in Japan by Mitsubishi researchers. So it's been promptly released in some part and patented in some other parts. Being a university and not wanting to work with someone else's patented technology, which I couldn't afford, what I did was to rework the algorithm in a way that still makes sense mathematically, which is more suitable to my problem, and which is not covered by the original patent. So the Smart Sifter Z algorithm is basically a very, very similar thing to what you find described in the Smart Sifter papers, plus some modifications that you find if you look at my scientific papers. There's all the gory mathematical details that I cannot really discuss here. Then there's another very, very hard problem we are looking at here. A network packet usually, as you know, carries an unstructured payload, which is structured if you look at it decoding the particular transport and application layer protocol you are using. But if you look just at the bytes, it's something unstructured. The problem is that even my fixed Smart Sifter algorithm wants numbers or classes, but doesn't want things that are varying in dimension and that are of different structure. So you have two solutions. The solution that was used before my research was to discard the packet content. You just look at the headers, because the headers are convertible to numbers, and you can apply your favorite learning algorithm to those with minimal effort. Of course, this yields some results, in particular for instance, detection of denial of service attacks, port scans, this type of things. But in many attacks, the interesting data is in the payload. So if you don't look at the payload, you will never see these